my name is Nako Nakatsuka. I'm a fourth-year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we move on to talking about Stereocenter or Chiral Center nomenclature. And so we talk about absolute configuration, which means the spatial arrangement of groups at the stereocenter, which I'm just going to abbreviate as SC. And so the stereocenter can only have two absolute configuration. Only two absolute configurations. Again, I'm abbreviating it. And therefore, we only need two stereocenter designators. And to do that, we use con in gold pre-log system. This is also often abbreviated as CIP. And what this does is it assigns R or S designations to the two enantiomers. So now I'm going to show you how you actually do this nomenclature. So the first step that you do is you assign priorities. And this is based on atomic number. And this is the atomic number of all the atoms that are attached at the stereocenter. And the key is the higher the atomic number, the higher the priority. So let me show you an example. If I have this molecule, which is the same one we saw in the previous slide, oops. There we go. Let's see what the priorities would be. And so first off, let's figure out where the chiral center is. Is it this carbon? No, because it has one carbon and then three hydrogens, right? Is it this carbon? No, because it has two of the same hydrogens. What about this carbon? Yes, in this case, we have CH2CH3 as one big group that's attached to it. We have a methyl group, and we have a hydrogen, and we have a chlorine. So this is the chiral center. So even before assigning priorities, this should be like pre-step one. Figure out where the actual chiral center is. And so from here, let's figure it out. Hydrogen has the lowest atomic number of just 1, and so it's going to be the lowest. And so I'm going to assign a priority number of 4. Chlorine has the highest priority with an atomic number of 17, and so this is the highest. And so I'm going to give it number 1. So at this point, I'm going to draw a little star here to talk about number 2, which is when you have two of the same atoms in terms of atomic number. So this is a methyl group and this is an ethyl group, right? And in this case, they're both carbons. So number 2 says when atoms are of equal priority, then you move to the next set of atoms. So what does that mean? In this case, what is this carbon bonded to? It's bonded to one carbon and two hydrogens, right? So carbon, hydrogen, hydrogen. What about this carbon? This carbon is bonded to one carbon, but then three hydrogens. I'm sorry, this carbon is bonded to two carbons. So we have carbon, carbon, hydrogen, hydrogen for this guy, but then just one carbon and then three hydrogens for the methyl group. So since this guy has an extra carbon, which is higher in terms of atomic number, the CH2CH3 group is going to have a higher priority than the methyl group. And thus I'm going to number this as this being 2 and this being 3. Sorry, it's getting a little messy. So now, for part 3, what you have to do, and this is where your molecular models come in really handy, you have to view the lowest priority group So in our case, it's hydrogen, and this is often the case, and we want to look at it in the back. So now let me redraw this for you and make the hydrogen go behind. And then we have CH2, CH3, and then we have the methyl group, and then we have the chlorine. And so now you have to imagine this molecule with the hydrogen in the back. And now let me prioritize them again, 1, 2, 3, and 4. And then you can then assign the absolute configuration by drawing a circular arrow from the first priority to the second priority. So in this case, I'm going to go from the first priority to the second priority like that, and then from 2 to 3. Since the number 4 is going to be behind the page, so we don't care about it. So after you assign the absolute configuration based on the arrow that you draw, if it goes to the right, when the priorities decrease clockwise, it's called R. And R actually stands for the Latin term rectus, which means right. So that's a pretty good way to remember that when you see R, it means that the priorities go from the highest priority to the lowest priority to the right. On the other hand, if it goes in the opposite direction, the left, it's S. And the reason why it's S is because the Latin term is sinister, which means left. So in this case, for 2-chlorobutane that we were looking at, we're going from 1 to 2 to 3 in the clockwise direction, and so it's R. So I'm actually going to write this as R2-chlorobutane. So as you can see, whenever you see a stereocenter, you can designate an R or an S group by following these 4 steps. You assign priorities, you go to number 2 when atoms have equal priorities, and you move on to the next ones. You view the lowest priority group in the back, and then you draw the arrows. Again, viewing and visualizing the lowest priority group in the back might be a little difficult at first, so I really encourage you guys to use molecular models to actually build this yourself and see how the 3 highest priority groups look when you put the lowest priority in the back.